Alright, so let's start off by making a D flip-flop. So I'm going to go ahead and I'll save this, and then I'll make a copy. I'm going to call my copy D flip-flop. Save that. And so what does a D flip-flop look like? Well, let me call it D flip-flop. And it's going to have an input, which is D, an input, which is a clock, an output, which is Q, an output, which is Q bar. And I'm going to give this flip-flop, well, we'll just leave it like that for now. So this is a single D flip-flop. And let's get rid of all of this stuff here. So input D comma clock, output Q comma Q bar, and D and clock are going to be wires. Register Q, because Q is going to have to remember a value, so we use register when we want to remember a value, and that's usually going to code to some kind of flip-flop. And then I'm just going to say wire Q bar, because I'm just going to set up Q bar to be the complement of Q, so I'm just going to take Q, run it through an inverter to get Q bar. And then what's our actual action look like? Alright, so new statement here. The always statement, we can say always at, and we can say, for example, positive edge of clock, begin. And I'll put a comment here. The following should happen when the clock ticks from a 0 to a 1, positive edge. We could also say neg edge for a negative going transition. Alright, so this is not like an if statement, right? This is something that's going to happen when the clock ticks, but remember, it's got to synthesize into a piece of hardware, not something that, you know, continually checks the clock, and if the clock has changed from 0 to 1, then it runs some piece of code. It's hardware, right? It's not an algorithm. But what do we want to have happen when the clock ticks? We want Q to be assigned whatever the value of D is. And that's really all the action that has to happen. And then separately, we're just going to set Q bar to be not Q, so I'm just going to say assign Q bar equals not Q. Alright, so that should be a good module. Let's go ahead and stimulate it. So I'm going to register D comma clock, wire Q comma Q bar. Right, now over here I'm setting up Q and Q bar to be wires because they're outputs, right? Even though inside this module Q is implemented in something that has memory, to the test bench, right, we're just connecting the output of this flip-flop to these wires Q and Q bar just so that we can look at them. Alright, so make an instance of D flip-flop. So I'm going to say D flip-flop. And we're still going to call it D1, and let's just set it up like this. So D goes to D, clock goes to clock, Q goes to Q, and Q bar goes to Q bar. And then we don't need this message anymore. This is start of simulation. So let's simplify our code here. So what do we want to actually do in our simulation? Let's start off with clock is 0 and D is 0. And let's wait 10 nanoseconds. And then let's set the clock to 1. And let's wait 10 nanoseconds. and then set the clock to 0, wait 10 nanoseconds. Let's set D to 1 and wait 10 nanoseconds. And at that point, the output should be stable. And then let's set the clock to 1 and wait 10 nanoseconds. And then let's set D back to 0 and put in a bit of a delay. Set the clock low, put in a bit of a delay. Set the clock high, put in a bit of a delay, and that's the end of our simulation. Alright, so let's go ahead and see how this runs. So we got a syntax error right here at line 5. Alright, so line 5 of design is right down here at the input statement, but as usual, the error is actually in the previous line, no semicolon there. So put the semicolon in, try running this. So we made it down to line 32. There's a syntax error down here, so missing semicolon on that assignment statement. The other assignments look good. Let's try that. And there we go, we got some results. Alright, so I'll take off the test bench variables, and we'll just look at clock, D, Q, and Q bar. So, in the beginning, Q is undefined, and so Q bar is undefined until the clock ticks for the first time. When the clock ticks right here, that value of D gets loaded into Q, and Q bar is the complement. When the clock goes low, nothing changes. When the clock is still low and D changes, nothing changes, the output stays low. But then when the clock ticks again, the output down here, Q, matches the input D. And then D changes while the clock is still high, nothing changes in the output. The clock ticks low, nothing changes. But then when the clock ticks high again, the output changes low to match the input D. So this is exactly what you expect from a D flip-flop, right? Every time that the clock ticks from low to high, the output should match the input, and all the rest of the time the output should be stable. So right here the output went low. That was one clock edge. The next clock edge was right here, and between here and here the output was stable, but at this point the output matched the input D, which was 1. And then everything is stable on the output until the next clock tick. And at this point, the output matches the input D, which is low. So that's a D flip-flop. And Q bar, as you can see, is always the complement of Q, and that's just set up because we had this wire statement. So there's a good D flip-flop, right? Simple example of a sequential circuit whose behavior depends on past values of some part of the system. Alright, so one simplification you can make on your test benches is if we're only testing one module and we're going to use the same set of inputs over and over again, we can instantiate this module more simply. We can say D flip-flop, that's the name of the thing we want to instantiate. We can give it a name like U1, and then we can just list the things that we want to connect to these I/O ports in the same order that they're listed here. So in this case this would be D, clock, Q, and Q bar. And we don't need to do this business of naming the port that we're trying to connect to, right? By default, this first signal that we've named here will be connected to the first port in this D flip-flop, which happens to be D, and the clock will be connected to the second one, and so on and so forth. But if for some reason I wanted to, instead of using the word clock, I wanted to just call this CLK, right? I could say CLK gets connected right here, and every time that I refer to the clock over here, I can call it CLK. And then when I run this, that signal CLK will get sent to the second input. And so, here's the test bench variables, clock D, Q, Q bar. Here's the variables inside the actual unit under test. So, I can get rid of either set of these and look at the signals as they're being generated by the test bench, and there's clock D, Q, and Q bar. So this business of naming the connection something different, specifying what port they're being connected to by name, that's useful when you have a module with, like 20 different inputs to it, so we don't have to remember what's the 17th input supposed to be. But for simpler modules with just a few input and output ports, we can just instantiate it like this. That makes life a little simpler. Alright, so what's actually happening when we do this always block? If we say always at pos edge clock, and we say something like, Q is assigned the value of D. What does that synthesize as? It synthesizes very simply as a flip-flop, right? We create a flip-flop with a positive edge triggered clock. We connect the clock to here, and we have D going into the D input, and we have the Q output going to Q. And what this says is when the clock ticks, we should take D and copy it to Q. Well, that's what this does, right? When the clock ticks, this D flip-flop will load this incoming value, latch it in here, and that will come out into Q. So again, it's important when we're thinking about Verilog to think about what is being synthesized, right? What's the hardware look like that corresponds to this this set of code? So let me make another copy of this, and let's look at a counter. So let me call this count. And let's make a 3-bit counter. So I'll say 3-bit counter. And so I'll call this module count, and it's going to have a clock and an output, and I'm also going to give it a reset line. And the reset line is kind of just because the value of a counter depends on its previous value, and if we don't know the previous value, we don't know what we get when it counts up from there. So I'm going to put in a reset line just so we can force the count to go to something that we know. So our inputs are going to be reset and clock, and the output is going to be output, and it may not like calling this output, so we'll just call it out. So out's going to be a 3-bit bus, and reset and clock are going to be wires, and this output is going to be a register. It's going to remember its value. And so at the positive edge of the clock, we're going to do the following. If reset equals 1, then we'll set out to a 0. Otherwise, we're going to set out to out plus 1. So there's going to be our basic count module. And so to drive this, let's make an instance of our count U1, and we'll have clock out reset. Oh yeah, and I need a begin here. Alright, so when the clock ticks, it will check the reset line. If reset's 1, it'll set the output to 0. Otherwise, it'll set the output to its current value plus 1. So we've got our counter constructed, and we're going to need registers for reset and clock, and we're going to do wire, 3-bit wire that we're going to call our output, and then we're going to begin our simulation. So clock goes to 0, reset goes to 1. We'll wait 10 seconds, we'll raise the clock, we'll wait 10 seconds, we'll drop the clock, and we'll drop the reset line. And then we're going to loop 20 times. So I'm going to make my integer again here. And that's just for counting in the loop down here. So what are we going to do inside our loop? Let me put a wait in here. Alright, so I'm going to say for I equals 0, I less than 20, I equals I plus 1, begin. Alright, so what should we do in our for loop? Let's change the clock, which I'm actually calling clock. Let's set the clock to 1. Let's wait 10 seconds. And then set the clock to 0. And wait another 10 seconds. And then that's the end of our for loop. And that's going to be our whole simulation loop. Alright. So what's our test bench doing? It constructs an instance of our count module. It connects clock out and reset to those 3 ports. It starts off with the clock low, reset line high, raises the clock line, which should cause a reset to happen in the output, and then drops the clock and drops the reset. And then 20 times we're going to raise the clock, wait a little bit, and then drop the clock. And we'll do that in a loop. And if we want, we could, put a display in here. Well, let's just run it like, let's go ahead and add a display. So we'll raise the clock, we'll drop the clock, and then we can say count equals %d, and we'll output the value of out. Right? And nothing in here is modifying the value of out. The reason out is being updated is because out is connected to the second port of our count module, and in the count module, when the clock ticks, we'll find that the output gets incremented by 1. So let's save that and run it. So we have a number of errors starting at line 21 in our design, right here at end module. So I'm missing some sort of syntax somewhere. And I need an end which goes with this begin up here. Alright, so that's the end to go with that begin. This is a big if then else statement. If reset's 1, then do this, otherwise do that. So let's recompile that, and when you're debugging compile errors in your code, start with one error, fix it, and then go on and try to fix the others. So line 31 in the test bench, something it doesn't like, and this is our old favorite error, just a missing semicolon. So we'll go ahead and fix that and run it, and we've got our waveform loaded. Now if we go back and we look at our output, we can see what happened. Count went to 1, 2, 3, 4, 5, 6, 7, and then after 7 it went back to 0. Count it back up to 7 and 0, 1, 2, 3, 4. So let's look at our waveform, and I'm going to take out our integer I, because that's just a variable in our simulation. I'm going to take out these things in the module. So we basically have a clock, we have an output bus, which is 3 bits, and we have a reset line. So here in the beginning, right, our reset is high, but the clock hasn't ticked yet. So our output value is listed as X, unknown. Right here, the clock ticks, that resets the count, and the count becomes 0. Negative edge of the clock, and then after the next positive edge, the count is 1, and then over here the count is 2, and 3, and so on. And you can see the value of the count is being displayed next to each waveform. And this is a 3-bit bus, so if I expand that, we can actually see the individual bits. And this pattern that we saw when we looked at, building a counter out of T flip-flops, this least significant bit is toggling very quickly. The next bit toggles at half the frequency, and the most significant bit toggles at half of that frequency. And so at any point, for example, right here, the output value is 5, 1, 0, 1. The next clock tick, that 1 changes to a 0, and that causes the previous bit to toggle from a 0 to a 1. The most significant bit stays a 1. And over here, we're at all 1s, and on the next clock tick, all 3 bits toggle, and we go back to 0. So that's a counter. Alright, so let's save that, and let's make a copy, and let's look at one more circuit, which I'm going to call shift. And we're going to implement what's called a shift register, and this will be related to one of the questions on your lab 7. And this brings about an interesting aspect of the parallelism of Verilog. So let's take a look first of all on paper at how we would go ahead and implement a shift register and what a shift register does. So the basic idea is if we have something like a D flip-flop, let's imagine a series of these, and suppose we take the output of one flip-flop and connect it to the input of another flip-flop, and we have some original input and we have some final output, and still, we don't usually show the clocks. We understand all the clocks will be ticked in unison, but I'll go ahead and draw these for this sake. And so here's our clock input. And the question is, what happens when the clock ticks? So suppose originally that all of these outputs are 0. So our output looks like 0, 0, 0, 0. And if we have a 0 coming in the beginning, right, when this clock ticks, that 0 gets loaded in, the output stays a 0. This is outputting a 0, so this will input a 0, it'll stay a 0. So what happens if we change the input to a 1? Well, nothing happens till the clock ticks. But the next time the clock transitions from 0 to 1, this 1 will get loaded into this D flip-flop, and this Q output will become a 1. But what happens to this D flip-flop? Nothing. Because at the moment the clock ticks, this was a 0. Now, shortly after the clock ticks, 5-10 nanoseconds later, this output becomes a 1. But at the moment of the clock tick, all of these Q outputs are 0, so all of these D inputs are 0, so these stay as zeros. But then, a few nanoseconds later, this Q output becomes a 1. So what happens on the next clock edge? Well, we have another 1 coming in here, so this becomes a 1. This 1 on the D input gets loaded into this flip-flop, and this becomes a 1. And the output here becomes a 1. But at the moment that the clock ticked, this was still a 0. So we still have a 0 going into here, and a 0. And now if we change the input to a 0 at the next clock tick, that 0 will get loaded into here, and this will output a 0. But at the moment of the clock tick, there was a 1 going into D, so that's a 1. There was a 1 going into this D, so that's a 1. And there was a 0 here. And then after the clock tick, this is outputting a 0, this is still a 1, this is a 1. And at the next clock tick, well, we have a 0 going in, so that's a 0. 0 going in here is a 0. 1 going in here is a 1. 1 going in here is a 1. And so you can see what happened. For 2 clock ticks, we had a 1 coming in. Well, there's the first one, there's the second one, and now these two are moving down through the register, but after that second one we put a 0 back in, and that 0 is starting to work its way through. So this is a shift register. We have something coming in the beginning, and each time the clock ticks it moves down one stage at a time. This is also how we can make a delay circuit. So we use a simple version of this in Lab 6 to make our 2 to 4 second delay for the yellow light of our traffic light. And it was just a pair of flip-flops, and we drove the clock from a 555, 2 seconds for each clock tick, and each time it ticks our input value moves down, and so we had our old green and our delayed old green signal coming out like this. This is also sometimes called a bucket brigade circuit, and you can have hundreds of these, and the sense is you put something in over here, and each time the clock ticks it gets passed from one of these blocks to the next to the next. This is how people dealt with fires. You'd form a line of people, and you'd pass a bucket to the first person with water, they pass it to the second one, and so on, and so you can convey the water down to where the fire is. This is also how you can make a delay effect for something like a guitar. You take your signal, you digitize it, you put it in here, you clock it slowly so that it takes maybe 500 milliseconds for your signal to get from here to here, and then over here you turn it back from a digital signal to an analog, and you get a delay on your signal. You mix it in with your original signal and you've got an echo effect. Bring it back here and you can get a reverb. So so lots of uses for this. So this is an easy way to make a shift register out of D flip-flops, and this would be a 4-bit shift register. And so if we create 4 D flip-flops in Verilog, we could set up the output of one to go to the input of the next, and so on and so forth. We can implement this circuit in Verilog. Alright, so how can this work? Well, let's make a 4-bit shift register. So I'm going to make a module called shift, and it's going to have an input, output, a clock, and we don't need a reset because once we feed a value into the beginning, that will get shifted through. So inputs are in and clock, and output is out. And I'm going to make all of these things wires. Wire in, comma, out, clock. Alright, so let's imagine 4 D flip-flops inside. So I'm going to call these things D0, D1, D2, D3. So these are the 4 stages of our shift register. And so on the positive edge of the clock, what are we going to do? Well, we're going to do the following. We're going to take D0 and we're going to copy it from the input, and we're going to set D1 equal to whatever is in D0, and D2 whatever is in D1, and D3 whatever is in D2. And then I'm just going to use an assignment statement to say out equals D3. Alright, that's kind of taken straight from our picture, right? We've got an input bit coming in here. We're going to, when the clock ticks, copy that into D0, copy D0 to 1, 1 to 2, 2 to 3, and then we'll always make our output equal to whatever D3 is. So we'll just take the value from flip-flop D3 and copy that to our output port. So our test bench is going to work as follows. We'll have register in, comma, clock, and wire out. construct an instance of shift, and we'll feed it in, comma, out, comma, clock. Alright, so we're going to still use a loop. We're going to loop, let's keep looping 20 times. But let's set our input value, and we're going to set our input value to be something random. So I'm going to say $u random, which gives me a positive number or a 0. And I'm going to say u random %2, which says pick a random number between 0 and 1 inclusive. So in is going to be either a 0 or a 1. And then I'm going to tick the clock high, and then I'm going to wait 10 nanoseconds and then tick the clock low, wait another 10 nanoseconds, and we'll take out this display. And so we'll go through 20 clock ticks with random bits going on to the input, and we'll take a look at what the output looks like, and we'll also take a look at what's going on inside our shift register with these values D0, 1, 2, and 3. So let's see how we do compiling this. So it doesn't like line 5 in design, which says input. So we've got the semicolon on module. So go ahead and run. And doesn't like line 7. So this should be wire in is the name of the wire. Int is a reserved word. So wire in out clock. Now again, I'm going to fix the first error, and then I'm going to recompile and go back and see what the errors are, because sometimes fixing one error will take care of others. Alright, test bench line 9, integer I. So I forgot my semicolon after instantiating the shift register. And here's an error at line 25. Alright, so subtle error here. We really need semicolons after these time statements. They're optional but not optional before the end statement. So previously I had a display statement in here, and that was saving us from seeing this error. We'll put semicolons on these time steps, and also let's go ahead and use this, always use this less than sign equal when we do these assignments to registers. So if we set that up and we run it, it'll compile it, it'll run it, it'll show us a waveform, and here's what our waveform looks like. So let's go ahead and let's move D0 through D3 and out down to the bottom. So let's put in up at the top of our display so we can see this randomly generated bit value that's going in. And let's say get signals, and I'm going to add D0 through D3 and out to our display. So you can see each time the clock ticks, something happens. So our D values begin 1, 2, and 3 are unknown, and slowly they get resolved. And our input value was originally low, and that slowly worked its way through to D3, which was our output. But then on the next clock tick, our input was high, and that high value worked its way through. And you can see we had a big long high pulse like this. Well, there's a version of it delayed 1 step, delayed 2 steps. And this low value here on the input eventually goes through and becomes a low value here and here and here. So this is a shift register, right? The input value is being slowly shifted through and appears in the output. So here's our original input, there's our output. Here's where the input was high, there's where it appears on the output. And then we have a low pulse followed by a short high section. Well, there's the low pulse, short high section, and then another low pulse right here, which comes out here, and so on. So that's a working shift register. So something to consider in this code here, why does this work? So if you've ever tried to do this in software, you would look at this and decide that this code is not going to work, because what's happening here, we're saying take the input, copy it to D0, take D0, copy it to D1, copy 1 to 2, 2 to 3. Well, you know, if this was a programming language, we would say, what's the value of D0? It's the same as in. And then down here, D1 is set equal to D0, which is in. D2 is set equal to D1, which is in, so D2 is equal to in. And then D3 is set equal to D2, which is in. It looks like in would take over all 4 of these values. But that's clearly not what happens, right? When the value of in changes from 1 to 0, it only goes through 1 flip-flop per clock tick. And it takes a number of clock ticks before it hits that D3 register. And that's because these statements are all happening in parallel, right? This is hardware. We're not saying do this thing, and then do this thing, and then do that thing. We're saying build me a piece of hardware which sets D0 equal to in, and D1 equal to D0, and D2 equal to D1, and so on. So it's synthesizing to a block of hardware which performs these actions in parallel when the clock ticks. Right, so that's an example of where thinking about this as hardware rather than an algorithm is going to be important. Alright, that should be enough to get you through most of the homework questions and most of the labs. You still want to go back and read this this guide that talks about Verilog, so the intro to Verilog programming. This is loosely what I've been following in here, but there's a lot more information in here than there is in the video. But this takes you through a lot of examples. It talks a little more about this arrow that we're using and why you should never use this single equal sign for assignments to registers. Talks a little more about test benches, and then here's an interesting experiment you can try to explore glitches related to timing, and so you can try that. And then it also talks about state machines, and I'm not going to go through a state machine example in here, but once you've gone through the first few practice problems, you should have everything that you need to implement a state machine. And here's an example that shows you how you could build something that does counting in gray code with a input for run or pause, right? So if we put this input to a 1, it moves from state 0 to 1 to 2 to 3 and back to 0. At any point, if that input becomes a 0, it just stays in that state. And in each state, you can see what the output is. And here's some code that will implement that state machine. And I introduced the parameter keyword, which is a way to just set up a symbol that stands for, in this case, S0 stands for 0, 0, S1 stands for 0, 1. So we can use these symbols, S0, S1, to stand for these bit patterns. And then when the clock ticks, if the reset line is high, we set the state to S0. Otherwise, we look at our state, and we use a case statement. So if you've done programming in C or Python, you know about case statements or switch statements. So this basically says look at state. If state is equal to S0, then do this stuff. If it's equal to S1, do this stuff, and so on. And so this is just a translation of what's happening up here. If we're in state 0, we want to either stay in S0 or go to S1, depending on the value of our input, which is this run pause signal. So if we're in state S0, if run pause is 1, set our state to S1, and set the outputs to, the output value for state S1. Otherwise, we don't do anything, which means we'll just leave our value of state exactly as it is. So you can read through that, and you can try this code. You can drive this code with a clock, and this statement will every 5 nanoseconds replace the clock with the complement of its value. So that's something you can mess with. Alright, last thing I want to talk about is FPGAs. So we're writing Verilog code, we're writing something to drive it using Verilog, and then we're running it through this simulation tool that shows us what it would do if we actually ran this circuitry, and it shows us timing diagrams. But most software that deals with Verilog also has the ability to take the resulting compiled description of our circuit and use that to program something called an FPGA, a field programmable gate array. And FPGAs, you can get them on development boards like this, and basically it's a small chip like this one right here, made by a company called Xilinx in this case, and it's got a whole bunch of logic inside. It's got multiplexers and demultiplexers and input and output ports and so on, and by loading values into memory inside this chip, we can connect components together. And we can say, for example, we want to take the output of this multiplexer and connect it to this output pin. And we want to take this input pin and feed it to the select line of this multiplexer. We want to take these two input pins and feed them to the I1 and I3 inputs on this other multiplexer. And you can wire up all these components internally. And this your Verilog tool will figure out for a particular type of FPGA how to program it to implement a circuit that you design in Verilog. And so you can actually create a physical piece of hardware that performs some action, like, you know, being a 4-bit counter, or, you know, being an arithmetic unit, or something that you know, plays a video game, or whatever it is you like. And so you can get these development boards, and there's a lot of these with a lot of different features to them. But you know, this board contains an FPGA in the middle, and then it's got various peripherals. It's got some 7-segment displays that are connected to certain pins on this device. It's got some push buttons that are connected, some slide switches that are connected. There's also a VGA port, so a 14 or 15 pin output that you can plug into a VGA cable to an old style monitor, and a USB bus, and you can get these with you know, HDMI ports and RJ45 jacks for networking, and all kinds of gizmos and gadgets. And basically you mostly connect to this through a USB port and run software from whoever made this board, and it takes your Verilog code and compiles it and then turns it into programming instructions, and then you can dump those instructions through a cable to this board and actually configure this piece of hardware. And it's non-volatile. Once you do this and you take away power, you throw this in the drawer, pull it out next week, it's still programmed to do whatever function you programmed it to perform. And so this is how a lot of custom chip development is done. Instead of designing a custom chip that's manufactured in a foundry out of silicon, people use FPGAs, programmable gate arrays, and it's cheaper. It's reusable. If you make a mistake, right, if you forget, you know, to set something to the right value in here, and you miss it in your simulation, you get your chip and your circuit's not working, you don't have to throw the chip away, right? You just fix your code, retest it, reprogram the device. If you do this on a foundry, right, that's a multi-million-dollar mistake. And so these are great for reuse, they're great for rapid development, and it's actually Cisco that helped popularize FPGAs in the industry, because when Cisco was developing its first routers, they couldn't afford to have custom chips made, and so they did something very risky at the time. They used FPGAs. Well, when the network took off and everybody started buying Cisco routers, there was a lot of FPGAs, and it pumped a lot of money into the industry, and FPGAs took off and became more and more the dominant way that people do custom chip design. So this is a big part of the world, and it's driven largely by Verilog. Alright, so that's kind of a quick overview of a lot of different aspects of Verilog and hardware design, and how, you know, kind of more modern engineering works in the digital circuit realm. Lots of problems to work on in the practice problem set. Lab 7 does more Verilog, and the last class, well, the next class after this one, we'll play around with some more Verilog. So that's almost it for the course. We've got one more topic to discuss, and that's going to be a discussion of different types of more advanced circuitry arithmetic units, logic units. We'll talk a little bit about fast algorithms for doing things like addition and multiplication. This is just kind of rounding out the body of things we've been discussing. So we'll do that in our last lecture. All right, thanks.